right, now that we've talked a lot about natural climate changes and how those may be accounting for some of the warming that the Earth has experienced over the last 150 years, or spoiler alert if you haven't watched them yet, how it doesn't really account for much of it. Now we're going to talk a lot about what we have done to the climate system and how we have changed it. And you'll actually find that the evidence is pretty compelling, and in my opinion, this is a lot more plausible of an argument for climate change. So let's do it. How we are the problem. So, first off, what is actually causing global climate change? What is the smoking gun? What is the main thing that's causing all of this? Well, it goes to an interesting effect that you feel every single day when you step into your car on a hot afternoon. And those of you who drive, you know what I'm talking about. Or those of you who have jumped into a car on a hot afternoon, you know what I'm talking about. The idea behind the greenhouse effect. So think about, you park your car, let's say you're going to class and it's 11 o'clock. You park your car in one of the parking lots and it's sitting out there in the sun. And sunlight is transparent, or your windows, the windows of your car are transparent to sunlight. So sunlight passes right through them. It then gets absorbed by the interior of your car. As a result, the interior of your car begins to warm up. As it warms up, it begins to give off more long-wave radiation, more infrared radiation. Unfortunately, those windows that were transparent to sunlight are not transparent to that long-wave radiation that your car is giving off. Instead, they are opaque to it. They absorb it and emit it back to your car. Therefore, in a real sense, heat is getting into your car, but it's unable to get out. And hence the temperature of your car heats up, heats up, heats up until you're done with your class, you jump into your car, and it's a lot hotter than it would otherwise be. It's a lot hotter than it would otherwise be. Greenhouse gases behave the exact same way. They let sunlight in. They are transparent to sunlight. But the infrared radiation that Earth gives off is absorbed by them. They're opaque to it. So they let heat in, but they don't let it out. And this is important because this throws our Earth's energy balance off. That then results in our Earth warming up until a new balance is achieved. This is exactly how greenhouses work, hence the name greenhouse effect. So, what gases behave like this? And this is a little bit of review from things we've already talked about. Now we'll talk about what we've done to these gases, but the four most common gases are water vapor, methane, carbon dioxide, and ozone. So water vapor, methane, carbon dioxide, and ozone. Let me talk about each one of these for a second. Okay, water vapor. Water vapor doesn't hang around in our atmosphere. It quickly either condenses into clouds and rains back down, or it moves somewhere else and then condenses and rains back down, or at night it condenses and forms dewdrops and then it re-evaporates the next day. All of that to say, water vapor doesn't hang around in our atmosphere very long. It doesn't hang around. And water vapor also varies greatly from location to location. There are some locations where you're having bad hair days and humidity is really high. As a result, water vapor is really high. On the other hand, you have other locations where anything metallic you touch causes a shock, and boom, water vapor is really low. So water vapor really isn't the problem here. Now what about ozone? Believe it or not, near the surface of the Earth, ozone behaves like a greenhouse gas. Here near the surface of the Earth, other than ultraviolet radiation, much of incoming sunlight is passed right through ozone. Thankfully, it blocks that bad stuff, the bad UV radiation, but much of the rest of the sunlight it allows in. Well, ozone actually absorbs a lot of long wave radiation that the Earth is giving off, so it can behave like a greenhouse gas. Now, here near the surface of the Earth, though, ozone actually reacts in and reacts out of the atmosphere very quickly via what's called photochemical smog. Essentially, what happens is every morning our cars and the tailpipes of our cars spit out nitrous oxides, which then react with sunlight to give off ozone molecules. Those ozone molecules are very unstable. They then break back down and the cycle is complete. So ozone doesn't hang around for long either. However, these other two gases, methane and carbon dioxide, are much more concerning. Much more concerning. And in fact, make sure you write this down, double underline it, put it in red, box it, get a tattoo of it if you have to. The one we are most concerned about is carbon dioxide. And the reason why is because, one, it's had the greatest increase, and two, it sticks around for the longest time. When a carbon dioxide molecule gets above the surface of the Earth, it can hang out there for over 100 years. So we're very concerned about it. Methane we're also very concerned about. Its concentrations are much lower, and it hasn't experienced as dramatic an increase, but methane is very potent. So we'll talk about that in a moment. Let's talk about carbon dioxide though. So carbon dioxide concentrations have actually been recorded over the past roughly 65 years. And in fact, many locations, even here in San Jose, have carbon dioxide monitors to look at local carbon dioxide fluctuations. But when we talk about carbon dioxide in the atmosphere, we don't like to look at it here near sea level. And especially in urban centers and in cities, because in these regions, carbon dioxide concentrations can vary wildly throughout the day. However, once you get into the free atmosphere, higher up into the atmosphere, so above 1,000 meters above the surface of the Earth, as you get higher up and as you get into more isolated locations, carbon dioxide is said to be well mixed. And what that means is that carbon dioxide concentrations don't vary much from location to location. And the variations are very small. So what we want to do as climate scientists is we want to measure carbon dioxide concentrations high in the atmosphere and in isolated locations, locations where there's not a lot of urban activity, locations that are relatively low population centers, and as a result, we want to look at very remote locations. The textbook location, the big location, is Mauna Loa in Hawaii, on the Big Island of Hawaii. The Big Island of Hawaii is in the middle of the Pacific Ocean. It's a relatively small island, so it's pretty isolated. And while there are cities in Hawaii, Mauna Loa is 11,000 feet above sea level, so it's high above those cities. Very few people live around there, so it's actually an ideal location to measure carbon dioxide concentrations. And it's also high in the atmosphere. Again, it's 11,000 feet above sea level, so it's getting that well-mixed air. So it removes any of the signals from human activity or from day-to-day industrialization. It removes all of that. And we're just looking at the baseline. So that's why we want to do that. Well, at the Mauna Loa Observatory, there is an agency associated with the Scripps Institute for Oceanography, and a gentleman by the name of David Keeling started recording carbon dioxide concentrations at Mauna Loa. And what David Keeling realized is that carbon dioxide concentrations were steadily rising. And in fact, carbon dioxide concentrations have actually risen pretty substantially. And I'll actually show you David Keeling's curve. It's now referred to as the Keeling Curve, to show you how carbon dioxide concentrations have changed. Well, in the late industrial periods, so right around 1850, right as industrialization was really getting going and cities were beginning to develop and industrialization was really going, carbon dioxide concentrations were around 280 parts per million. So a part per million is if you take 1 million molecules of atmosphere, throw them on a table, and count out how many of them are carbon dioxide. In 1850, it was 280. It is now 400. That's a relatively large increase when you actually consider that's a 120 part per million increase, and that's about a 45% increase in 150 years. That's a major increase over a short period of time. But we can even see this more detailed since the 1960s, since David Keeling's observations began, and they're graphed on what's called the Keeling Curve. And the Keeling Curve shows an increase, a general increase in carbon dioxide concentrations. One thing I want to highlight here, if you look at this image, you notice that carbon dioxide readings actually go up and down throughout the year. I always like to call this the Bart Simpson's hair analogy. They look like Bart Simpson's hair almost. They rise during one time of the year and then sink during another time of the year. Well, the reason why this happens is because of seasonality. During the spring and summer months, there's a lot of plant activity, and plants take in carbon dioxide. So during those months, carbon dioxide concentrations decrease slightly. And then in fall and winter, as trees shed their leaves, they begin to hibernate. That causes carbon dioxide concentrations to go back up. So we see increases during fall and winter, decreases during spring and summer, and then increasing, decreasing, and so on. And you see this signal every single year. But if you were to take a look at the overall trend is substantially higher. I mean, we're talking at the beginning of David Keeling's observations, carbon dioxide concentrations of around 315. And this actually isn't the most recent reading either. Current carbon dioxide concentrations, and I'll actually correct this here, current carbon dioxide concentrations are actually more like 408. Again, it depends on the time of the year, though. They're actually closer to 408. So really, in the last 55 years, 65 years, more like it, in the last 60 to 65 years, we've seen carbon dioxide concentrations rise from 315 to 408. That's a lot, that's a big change over a relatively short period of time. And if you actually compare this to even previous carbon dioxide concentrations taken from ice cores, this sudden and drastic change has all happened in just the last 200 years. This is what is so concerning about climate change. This is why we're so worried about it. Because these changes, this major explosion in carbon dioxide concentrations has only happened in the last 200 years. And it's happened during the period of industrialization. Coincidence? I think not. There's one other really concerning fact, and that is there is a very strong correlation between carbon dioxide concentrations, which are shown in this map here, or shown in this graph here, and air temperature. And what you actually notice is every time carbon dioxide concentrations are high, air temperature jumps up. And every time carbon dioxide concentrations are low, air temperature is low. And so there is a little bit of a chicken before the egg, correlation versus causation, but there's clearly a relationship between temperature and carbon dioxide concentrations. One of the other things I should highlight here is this graph here only puts carbon dioxide concentrations at around 300 parts per million. Actual current measurements are way up here at around 400 parts per million. So we've actually seen a huge increase in a very short period of time. That's very concerning for us. Now, the greenhouse effect is a good thing. We want greenhouse gases. I'm sure you've heard up to this point in your life, man, greenhouse gases are bad, greenhouse gases are horrible. Al Gore's probably talking about how bad greenhouse gases are and how we need to get rid of them and they're evil. But actually, they're good. Without greenhouse gases, the average temperature of the Earth would be 59 degrees Fahrenheit lower than it currently is. So think about that. Think about the day you're experiencing right now. And I mean, this is a very crude example, but it's a good thought experiment. Subtract 59 degrees from it. How would that change what you're wearing? How would that change the activities you're doing during that day? It would have pretty profound changes, right? I think so. I mean, right now as I'm recording this, the temperature outside is around 70. And if I were to subtract 59 degrees from that, that gives us a temperature of 11. 2 very different days would be planned in that kind of weather. So, yeah, so this is a big deal. However, have you ever heard of too much of a good thing? Think about your favorite food. Imagine if you ate it for breakfast, lunch, and dinner nonstop. It wouldn't be a good thing for much longer, would it? So yeah, that's something that we are concerned about. Too much of a good thing can have dire consequences. More greenhouse gases result in more heat trapped in, which results in warmer global temperatures. So the more greenhouse gases we have, the hotter we get, and that's what's happening right now. Again, without greenhouse gases, we'd be much colder. With them, we're nice and toasty. But again, the more greenhouse gases we have, the more heat is trapped in, the warmer we get. Now, I've focused mostly on carbon dioxide, but I wanted to mention a couple of things about methane, too. Methane is a very potent greenhouse gas. And in fact, methane is 21 times as potent as carbon dioxide. Here's what that means. If I had 2 molecules side by side, one carbon dioxide and one methane, methane could absorb 21 times as much energy, 21 times as much heat as one molecule of carbon dioxide. So methane definitely has an important greenhouse effect. However, methane hasn't been increasing as dramatically as carbon dioxide has. But how has methane increased? Well, there's a few ways that methane has increased. Mostly due to agriculture. We here in the United States are a very beef-loving culture. We love our beef. We love cow. And cows are a major source of methane. And they both burp and fart it out. You can feel free to laugh at that, but it's true. They both burp and fart out methane. And, well, in the last 150 years, we have cleared out a lot of forests and replaced them with cow farms. So we've gotten rid of something that was taking in carbon dioxide and instead replaced it with something that's giving off methane. No, cows aren't the only source of methane. Agriculture isn't the only source. Oceans have methane in them. A lot of ice has methane trapped in it. And then we are also a source of methane. Methane is also referred to as natural gas, and one of the things you may hear a lot about is using natural gas, burning natural gas. And the idea is that if we allowed it to be released into the atmosphere, it would be much more dangerous than if we burned it and converted it to carbon dioxide. So, with all of that said, I've already mentioned this, but I'm going to talk about it again. Based on everything, based on looking at all the climate signals, based on looking at changes in carbon dioxide and methane, looking at other natural events that have happened in the last 150 years, looking at things like solar radiation, the Earth's position relative to the sun, continental drift. After putting all of that together and looking at natural changes compared to human changes, the Intergovernmental Panel of Climate Change has actually come out and said it is extremely likely, and this is actually with an over 97% certainty, that at least some, if not most, of the previous warming that we have experienced is caused by human activity. And that total warmth, that we talked about this in the last lecture, is between 0.85, give or take 0.2 degrees Celsius. And that means that the overall change has been between 0.65 and 1.05 degrees Celsius. The overall change has been between 0.65 and 1.05 degrees Celsius. That's a relatively major change in a relatively short period of time. Relatively major change in a relatively short period of time. Now, how bad can it get? Well, obviously we can't predict most natural events. We can't predict most natural events. There could be a major volcanic eruption. There could be something else. Now, we can say that continental drift is going to have practically no impact. The sunspot cycle is relatively predictable, and it doesn't have a major impact. The Milankovitch cycles take way longer. So, forecasting future climate changes really are based on changing the amount of carbon dioxide in the atmosphere and seeing how the Earth responds to it. Well, we can't obviously do this with the Earth that we have. We can't experiment with the Earth that we have because that would take too long and it's too large scale. But what we can do is we can model the Earth similar to the way that we model weather. We can model the Earth and take all of those different things into account. Take agricultural work into account, take continental drift into account, take ocean currents into account, take ice distribution into account. We can take all of the individual components of Earth's system into account and then change carbon dioxide and see how that changes Earth's temperatures. And we can do that using a series of what are called global climate models. And in fact, as I'm speaking right now, the United States has just released the newest edition of our global climate model called the Community Earth Systems Model. And if you're ever bored and are looking for a good night's sleep, a good night read, look up Terrence Mullen's master's thesis. I actually did some work on that climate model. And I can tell you these things are pretty accurate. With that said, let's talk about the scenarios that they're predicting. So all of these scenarios are based on the average temperature in the last 20 years of the 20th century. So 1980 to 1999, that's our baseline. Okay, that's our baseline. Well, we've looked at different scenarios run through this climate model and other global climate models done by other nations. And this is what we've come up with. The first scenario is if we were to leave carbon dioxide constant, so no more increasing, we would still, from 1980 to 1999, from that average, we would still see an additional third to almost 1 degree warming, so 0.3 to 0.9 degrees warming. So the bad news is we are already committed to additional warming. If we stopped emitting all right now and no more carbon dioxide and concentrations leveled off, this is what we would see. This is obviously not going to happen. What is likely to happen? Well, there are one of 4 scenarios that have been mapped out by the IPCC. And here they are. The first set of scenarios are called the A scenarios. These scenarios are focused on economic growth. And the idea here is we are going to focus on growing our economies rather than focusing on climate sustainability. So it's all about growth. It's all about more output, all about more economic prosperity at any cost. We're not worried about the climate. Well, the A scenarios can give us one of 2 categories, either globalized efforts or localized efforts. And we can actually split the globalized efforts into one of 3 scenarios. The first scenario is a fossil fuel intensive scenario. This is called the A1F1 scenario. In the case of an A1F1 scenario, meaning that we as a world, we are going to globalize our economy and we're going to do it by any means necessary, even if it means burning all these fossil fuels, that would see a minimum of 2.4 degrees and a maximum of 6.4 degrees Celsius in warming. If you watch that documentary, 6 Degrees Could Change the Earth, you'll see that 6 degrees of warming is a really bad scenario. A really bad scenario. The second effort is what's called the A1T effort, the A1T scenario. And this is focused on, okay, we're going to grow economically, but we're not going to use fossil fuels at all. Here we're going to do all electric cars, all wind energy. We're not going to focus on fixing things. We're just going to focus on not using fossil fuels anymore. That gets us 1.4 to 3.8 degrees warming. So that's still a lot of warming, but that's not nearly as bad as the A1F1 scenario. And then the balanced scenario, and this is the one I think would most likely happen, is the A1B scenario. This is the hybrid car scenario. This is realizing that fossil fuels do play a role in our economic growth, but also realizing that we need to get off of them. And we need to also use alternative sources. And so, like I said, this is like the hybrid car version. This is like the gas guzzler. This is like the Tesla. The A1B is like the Prius. And it's a balance between energy sources. And this scenario commits us to 1.7 to 4.4 degrees warming. So not as bad as the A1F1 scenario, but not as good as the A1T scenario. Any one of these 3 scenarios is going to cause warming. Now, as I mentioned, these are the globalized efforts. This is a global economy, focusing on global economic growth, a lot of international agreements, a lot of collaboration. The other scenario is, what if instead of focusing on growing as a global economy, we instead focus on growing locally and regionally? And so we do our own thing, China does their own thing, Japan does their own thing, Russia does their own thing, and we each do it our own way. So there's no global coordination. This is seen to result in as much as 2 to 5.4 degrees in warming. So this is actually worse than either the A1T or the A1B scenario, and it's almost as bad as the A1F1 scenario. And the reason why is because every nation is going to use their own means to grow. there's not going to be any kind of global efforts. And so we as a globe aren't going to say, okay, hey, we're all going to drive Priuses. Instead, one country is going to drive Teslas, another country is going to drive Hummers, another country is going to drive Priuses, and there's very little coordination between those countries. So that could result in some problems. Now the B scenarios, these aren't focused on economic growth. These have the mindset that, hey, economic growth is good, but we need to worry about creating a world that is sustainable, that is ecologically sustainable. And so rather than focusing on economic growth, we're going to focus more on stabilizing our climate. There are two scenarios here. The B1 scenario is globalized conservation efforts. These can keep warming down to 1.1 degrees Celsius, which I argue we could live with. And they could give us up to 3 degrees Celsius in warming. Now here's what I mean by globalized conservation efforts. Basically, we as a globe say, hey, we need to work on this together. We need to come up with a plan together. And we need to enforce this plan together. We'll actually talk about a few of these in a later video. And there are some that have been proposed. The second scenario, and this one looks very similar to the A1T scenario, are local and regional efforts. And the idea here is that we as a world decide, hey, we're all up for this, but I want to do it my way, you can do it your way, you can do it your way. The problem here is that climate change is a global issue. And in the case of a B2 scenario, everybody is doing it their own way. And so for some people, or some ways are more effective than others. So maybe the way the United States is doing it isn't as effective as the way that Belize is doing it, or the way that Brazil is doing it, or the way that South Africa is doing it. And so this can result in less effective results. And yet this is still not as bad as any of the A1 efforts. I mean, it's equally as bad as A1T, but it's not as bad. The goal that we have as climate scientists is to focus on a B1 effort. That's the best case scenario. That's the best case scenario. Now again, each one of these scenarios does have uncertainty, and that's why there's a range here. It could be as good as the lower value or as bad as the higher value. Many of the globalized efforts are to keep warming to within 2 degrees Celsius of these 1980 to 1999 averages. We're already halfway there, unfortunately. We're already at 0.65 to 1.05. We're already experiencing quite a bit of warming. So this is something we're very concerned about. Here are some of these scenarios from the IPCC compared to global temperatures, global average temperatures, and where things are going. And again, the biggest concern is coming up with globalized efforts to improve our climate system. And some of these globalized conservation efforts are